Hello and welcome. Today we're going to be looking at clastic reservoirs from a classic oil province, the North Sea in the United Kingdom. Back in 1959, the Groningen field was discovered in the Netherlands, and since then at least 16 billion barrels of oil and 145 TCF of gas have been found in and adjacent to the North Sea. The basin itself covers around 725,000 square kilometers, and it's bounded to the east by the Baltic Shield, to the west by the Scottish Highlands, and to the south by Hercynian metamorphic rocks. And the reservoirs range in age from Carboniferous to early Tertiary and include a wide variety of depositional settings. I've got 8 cores for you today. They're short cores, but they've been chosen to represent the widest possible range of settings, and they span the Carboniferous to the Jurassic in age. So the location where the cores come from, 5 of them come from the southern North Sea. There's the Groningen field over in the Netherlands, and then these cores are all sitting out in the southern North Sea. So we have 2 from the Permian and 3 from the Carboniferous. And then we have a further set of cores that come from the northern North Sea in the Brent area, and we'll be looking at those as well. And those are Jurassic in age. So the geology of the North Sea, it's floored by late Silurian Caledonian metamorphic rocks, and it's highly structured due to a lot of regional tectonic movements and by local salt mobility. And we can see here by this cross-section through the northern North Sea that we typically have these rift systems here, bounded by faults with highlands sitting to the east and to the west. The regional positive features divide the North Sea into several sub-basins, and they've influenced sedimentation. And faulting and regional unconformities juxtapose source rocks and reservoirs, and what that means is that you have a great chance for the reservoirs to be charged by the source rocks. Most of the gas is sourced from Carboniferous coals, and most of the oil is from the Jurassic Kimmeridge clay and other minor source rocks. And the associate periods of mountain building, the Hercynian and the Alpine mountain building, are associated with some volcanic activity as well. If we look at these 2 maps, we have the Paleozoic map here and the Mesozoic map here for the North Sea. And we can see, particularly from this Mesozoic map, that there's a great deal of complex tectonic activity going on. And we've got the interplay of 3 different fold belts within that area here. So the North Sea is surrounded by the red marker. So the evolution of the northern North Sea, the basic structural framework is the result of Upper Jurassic and Lower Cretaceous rifting, partly controlled by older structural elements. And we can see by looking at this map that we've got these rift systems coming down through here, another rift system extending onto Scotland, to the mainland, and heading down towards the south. So I'm not going to go through the whole table, but we can see there's a history that begins with major rifting with volcanism and deposition of aeolian sediments and fluvials. Then that's overlain by Triassic rifting, and then a basal marine transgression at the start of the Jurassic, which was then followed by the growth of a volcanic dome over the triple point in this area, sitting in here on the map. Then in the late Jurassic, there's major block faulting, which caused uplift and tilting and created a lot of the traps for the hydrocarbons. And then more rifting in the Cretaceous, followed by thermal subsidence. And then finally, we have mountain building in the Alps, in the Cainozoic, and the onset of seafloor spreading in the North Atlantic. And this leads to chalk deposition, followed by margin uplift and submarine fans. In the southern North Sea, which is the largest gas-producing basin on the UK continental shelf, we're producing from Permian sandstones, sealed by Zechstein salt, and there's a complex history of basin subsidence. And uplift events occurred, followed by crustal extension, which allowed the rocks to become folded and faulted. And the basin itself, this basin sitting down here on the map, is very much a saucer-shaped basin into which the sediments are prograded. And we see aeolian reservoirs and some fluvial as well. And the history of these rocks is a Variscan orogeny back in the late Silurian, early Devonian. And then in the Mesozoic, there was more rifting, and that allowed the opening of the Atlantic. And halokinesis, so salt activity, also helped to create these grabens around the basin margins within this saucer-shaped basin. It's pretty structurally complex, as you can see in here, with a lot of sub-basins created by the different tectonic events and tectonic elements. But what's also interesting to look at is that the age of these gas fields, we have the older Carboniferous gas fields in green on the outskirts of the basin, and then the younger Permian gas fields sitting in here in orange. And then finally we even have some Zechstein fields up here shown in pink, so that there's a range of ages of the gas fields within the basin. So the exploration history of the North Sea, after that discovery of the Groningen field, it led to the idea that the same play elements probably extended below the North Sea and as far as Scotland. And so the UK government were pretty smart. They subdivided the North Sea. They set up a boundary with Norway and designed the quadrants so that they knew where the boundary was between the two countries. And then the first discovery was the Western Sole gas field in 1965. But of more significance probably was the Ekofisk oil field, which was found in the Norwegian sector in 1969. And ironically, this was just a contract obligation well. They didn't even want to drill it, but it found 4.5 billion barrels of oil in fractured chalks. The next big discovery was the Forties field in 1970 with 1.8 billion barrels, and Shell had declined to farm into the Forties field, but they were rewarded the following year by finding the 3 billion barrel Brent field, after which Brent crude is named. Then they put in a lot of infrastructure, and the first UK oil came ashore from the Forties pipeline in 1975, and the government woke up and put the Oil Taxation Act into place to start earning some royalties from all of this oil and gas. And then finds continued through the 70s with pre-Cretaceous finds and some high pressure, high temperature fields. And then in the 80s, it was champagne time. Everything was going on, 1.6 million barrels per day production, a lot of exploration capital available, and a lot of privatization. If we look at this map here, we can see that this is the map from 1969. There's just a few wells that are drilled here on the North Sea shelf. And then as you go through the following years, all the way through to 2019, we can see that there's more and more wells being drilled, and these wells quite nicely define the different provinces, the southern, the central, and the northern North Sea. And then we gradually see the opening up of the Shetlands area as well. And then we can also see here that the technology in terms of platforms and many other things also evolved through time, from quite simple fixed platforms right the way through to these very complex spar platforms and straight attached leg platforms as well. The Piper Alpha disaster in 1988 with the loss of 167 lives was a very tragic event, but it did change the health and safety landscape for oil and gas forever. And then in the 1990s, it became a much more development phase. The west of Shetland was finally explored in very, very harsh conditions, and they found Clare, another 4 billion barrel gas field, oil field, and Foinaven as well. There were issues with the Brent Spar decommission, with Greenpeace occupying the rig, and peak production, as we can see from this graph here, occurred in 1999 for oil, and then in 2002 for gas. The Buzzard was the largest discovery in the 90s and remains the largest discovery since then at 1 billion barrels. The structure was recognized by several companies, but it took a bit of guts to go in and finally discover the field. So it's been declining since then, and this has led to a better fiscal regime, a creation of the Oil and Gas Authority in the UK, and there's a new wave of small private companies coming in now, and they're buying up these large fields and the satellites from the majors who are selling everything off and utilizing the existing infrastructure. So let's move on and have a look at some of the cores. And the cores, as I said, there's 8 short lengths of classic cores which were carefully selected to cover as wide a range of depositional settings as we could. So we'll start off with 3 carboniferous cores, A, B, and C, which are showing floodplain, crevasse splays, fluvial conglomerates, and sandstones. Then we're going to look at some Rotliegend core from the Permian, Aeolian sandstones, interdune deposits, and playa lakes. And then finally, we're going to look at the Middle Jurassic Brent group. So these are Storm deposits, Back Barrier Lagoon, floodplain, and a whole set of small samples from the Brent as well. And we'll talk about where they were deposited to. So the core locations, as I said, 5 of the first 5 are from the southern North Sea, from the gas basin. They're all sitting in here. And those are the 3 carboniferous cores and the 2 Permian cores. And then after that, we're going to move up to the northern North Sea and look at the Jurassic cores up there. So let's start off with Core A, which is from the Bolton field. This field was discovered in 1984 when gas was tested from the lower Ketch unit, Carboniferous Westphalian. Quite complex traps in a lot of these reservoirs. The well initially targeted Bunter sandstone, but with no shows, the well was deepened and encountered 345 feet of Carboniferous Westphalian fluvial deposits. And what we see in the core here, this is the core. 6 feet in length, and there's some very finely laminated sediments sitting in here, and some slightly rippled sediments sitting in here, and then a more cemented interval here with similar deposits. And I'm interpreting these as being most likely to be crevasse splays, and that explains these quite thick rippled intervals and the fact that we're not seeing nice trough cross bedding developed within these sediments. So an ancient analog for these would be the Cretaceous crevasse splays from Dinosaur Provincial Park, and we can see once again there's very nice climbing ripples sitting in here. And then a modern analog might be from somewhere like Kakadu National Park in Australia. So we've got quite warm, sultry conditions, humid, good, well vegetated, and these meandering channels crossing the plains. Now I said that these were crevasse splays, and I've got a nice picture here from the Mississippi, showing a crevasse splay here, which is about 1 kilometer across. And these are formed during flooding events. They deposit very quickly, and they're dominated normally by climbing ripples. They sometimes coarsen up as well, and with a lot of plant material in them as well. So these are the analogs. And this is what the log itself looks like. We can see some fining up here, suggesting that we have fining up cycles and probably dominantly meandering successions. And the porosity is pretty good, and permeability is good too, so nice reservoir. Moving on to the Hawksley field, and you can see from the map here, there's the Bolton field, there's the Hawksley field, so they're pretty close together. And what we've got here is a nice conglomeratic core. It's poorly sorted, so we've got some larger pebbles sitting in here and some very small pebbles as well, with the class ranging from subangular to well-rounded. And the matrix is a dark grey sandstone with several pulses of sedimentation. And the interpretation of these sediments is that we've got a basal lag in a fluvial channel, probably on a braid plane. And this is supported by the log character, which is not showing finding upward sequences, but is showing a fairly steady, blocky, spiky but blocky pattern. And looking at some ancient analogues, conglomeratic braided deposits from the Cretaceous Mill Creek Formation at Frank Slide, sitting in here, although these sediments, I would say the pebbles are a little bit more rounded in these deposits, but otherwise quite similar. And then a modern example might be something like a pebbly braided river near Selfoss in Iceland, and you can see these lovely braid plains and braid bars sitting here on the plain. The Hawksley field itself was discovered in 1998, and after an earlier well showed reservoir sands, but it was dry. And the well encountered gas, which is great, and despite drilling challenges, the field has produced almost all of its estimated reserves of around 430 BCF. And once again, they interpret this as braided river deposits as well. And the properties, as we see up here on the table, are really quite good. Moving to the Keister field now, which is close by the other two fields that we've already looked at. We start off, the exploration well encountered gas in Westphalian A and B sandstones, so in the Keister field, and also penetrated the gas-bearing Keister sandstone formation. And it's interpreted as low sinuosity fluvial channels. And when we look at the core, we can see some really nice trough crossbeds sitting in here. And my interpretation of these is that this is the channel portion of a meandering channel, overlain by point bars. And when you look at the well logs here, we can see that we've got these blocky sediments here, which would be the channel deposit itself. And then overlying that, you've got the point bar, which is finding up through this section of the core here. And ancient analog for this, we've got nice stacked trough crossbeds in somewhere like Dinosaur Provincial Park or in eastern Alberta. And a modern analog, there's many, many meandering channels around the world, but we've chosen the Williams River in Alaska. And then this chart here just shows stratigraphically where our three cores have been located so far. Moving on to the Rotliegend, the Permian deposits. First of all, we're going to look at the Alexandra prospect, and that's located quite near to the center of this southern North Sea basin. So we're in Permian deposits. It's in the same block as the Audrey field, which the next core comes from, and that field contains more than 1 TCF of gas. So the Permian Rotliegend unconformably overlies the upper Carboniferous deposits, and it's divided into the Limon sandstone, comprising clean sands, and then evaporites, mudstones and siltstones of the Silver Pit Formation. And the main reservoir sands were deposited in an arid environment. And when we look at the core here, we've got this possible interdune deposits here, these wavy laminated sandy beds. The sand grains themselves are very well rounded, and then they're overlain by this beautiful dune form. So here's the basal contact of the dune, and you can see the lower part of it, the beds are dipping quite gently, and then as you move up into the core, the planar cross beds steepen up, which is very typical of the base of an Aeolian dune deposit. So These are interpreted as aeolian dunes. The actual dunes themselves could be up to about 5 meters in thickness, and that's quite comparable with some of the ancient analogues. And I've chosen the lower Triassic Wingate sandstone here from Colorado. We've got a nice turkey vulture here for scale, and you can see this is very typical of all the way through Arizona, Utah, Colorado. We're seeing these beautiful blocky aeolian sandstones. And then a modern analog for fun, I've taken the aeolian dune from the Great Sand Dunes in Saskatchewan, not that far away from us here in Calgary. And you can see we've got these nice dipping beds here. This will be making our planar cross beds with some rippled sands on here due to the wind-blown nature of the sediments. And the porosities here are very good, 15%, and permeability is up to a Darcy, so a wonderful reservoir for producing gases. Moving on to the Audrey B field core, which is very close to the Alexandra prospect we just looked at. The main reservoir sands once again were deposited in an aeolian environment. But this time, as you can see, they're very different to those planar cross-bedded clean sands. And here we're seeing this quite muddy interval with a lot of contortion of the beds sitting in here. They're thinly laminated, they're mainly muddy in character, and possibly even some dinotubation or something in here as well. And I interpret these deposits as playa lake deposits. And a playa lake is a dry lake, or a playa. It's a basin or depression that formerly contained standing surface of water, which has since evaporated. And probably the most famous modern example of that is in Death Valley in Nevada. We can see these sandflats here in the lowest place in the United States, 86 feet below sea level. And then if we come down to look at an ancient analog, it's surprisingly, it's a bit challenging to find these in the literature. But the example I have here is from the Triassic of Morocco. We can see these laminated beds here with some waviness to these laminae again, so they're quite a good analog to what we're seeing from our playa lake deposits in the Permian. So now we're going to move on to one of the crown jewels of the North Sea, the Brent Group. And the Brent Group comprises one of the most famous reservoir intervals in the world. And it's been divided into 5 parts: the Broom, the Rannoch, the Etive, the Ness, and the Tarbert formations. And their initial letters spell out the word Brent. And these are all places that are located on the mainland. Generally, the Broom is interpreted as a fan delta deposit, and you can see here we have wavy laminated sandstone in our core sample, and that's overlain by hummocky cross-stratified sandstone of the Rannoch, which are interpreted as storm deposits in shore face setting, probably lower shore face to middle shore face. Then we go up into the Etive, where we have a planar cross-stratified sandstone, sometimes cross-bedded, which is interpretation is a coastal sandbar or barrier bar. And this is the main reservoir interval, and then we have another subsidiary interval of reservoir up in the Ness, with rooted mudstones and ripple laminated sandstones, and that's quite a variety of depositional settings within the Ness, suggesting that we're right on the edge of the lagoon, and with the creeks running down into the lagoon from the coastal section. And then finally the Tarbert is interpreted as a transgressive deposit, and a bit hard to see what's going on with this core because it's so beautifully oil stained. So there's a couple of models for Brent deposition, and one is that all of the sediments basically prograded towards the north, and this model was first published in 1970 based on 3 cores, 3 wells. So it's amazing that the model has stood the test of time right the way to the modern. However, I think that it's more likely that the sediments actually prograded in from the sides of the rifts, prograded out into the rift basin, and then were transported towards the north. And there's good evidence for that from fields like the Tern field, shown here, where we're seeing progradation directions definitely from east to west, and that's shown by the porosity distribution within the main reservoir intervals. This is showing a more detailed deposition of what happens with the sediments prograding out. So we've got the Rannoch formation here, the shore face deposits, the Etive stepping out over it with the barrier bars, and then the fluvial Ness, and then we have back stepping after that all the way up to the Tarbert formation here. So this would be a gradual transgression through time in the upper part of the section. Looking at two cores in more detail from this area. So these are from the Causeway Field, and the Causeway Field is a small Brent-hosted oil field located close to the Cormorant Field in the northern North Sea. So it was originally discovered in 1984, but it was a small satellite in those days and wasn't considered important. But now there's renewed interest in these smaller prospects. And in 2008, Antrim explored that an exploration well had intersected a 15-meter oil column, and the flow rate was up to 8,000 barrels a day. So they definitely went ahead, and now they're using the existing infrastructure to start producing. So this core here is from the Rannoch, and we can see that it's got this classic pinstriping that you see in storm deposits. We've got this hummocky cross-stratified and swaley cross-stratified beds sitting in here, which is just typical of storm deposits. And I've got an ancient example here, two ancient examples actually from Utah, from the book Cliffs. And this one shows the parasequence nature of these deposits, and we can see the individual parasequences here in the log. This whole section here is about 25 meters in thickness, and this ties into what the parasequences are showing here, where you've got a gradual progradation out over the deeper marine sediments, with the shallower marine sediments building out over the top of them. So that explains why we see this character here with these storm deposits sitting in this portion of the shallowing upward parasequence. And finally, we got core G from the Causeway Field, and this is Ness interval. And I said that the Ness was quite complicated depositional settings. And what I think we're seeing in here is rippled sandstones in the lower part, which are from Crete deposits. And then in the upper part here, we're going up into more muddy deposits that you can see there's some bioturbation sitting in here as well. There's a wavy laminae in there, quite a mix of sands and muds. And I think these are probably lagoonal sediments in character. So we're seeing the lagoonal sediments at the top, overlying these sandy deposits, the Crete deposits at the base. So if we look at the depositional model here for coastal lagoons in general, here would be our lagoon sitting in here, salt marshes and salt flats. We've got the creeks running in from here. And then when we come out into the more coastal portion, we've got the flood and ebb tidal deltas, barrier bars, which would be the Etiv sitting in here, and then going out into the deeper marine Rannoch formation sitting in there. And then you can also see, looking at where the core was taken through here, that we've got quite a range of environments within this very paralic setting. So as I said, the Causeway Field is just one example of these sediments, and the best example is without doubt the Brent Field, which is a 3 billion barrel field that's producing from these. In terms of analogues to these deposits, we've got a modern analogue from Australia, with strand plain sitting out here. So this would be our Etiv formation sitting out here, and then some lagoonal deposits in here, and some creeks running around and into them from the sides as well. So this would be the Ness sitting in there. And then an ancient analogue for the actual creeks themselves. This is from the Sandakan formation in eastern Borneo, Miocene in age, and we can see these small sandy creek deposits sitting in here that are running through the mangrove deposits. So just to summarize, the 8 chosen cores took us from the Carboniferous fluvial channels, crevasse blaze and overbanks, through Permian, arid Aeolian dunes, interdunes and playas, into the Middle Jurassic fluvial deltaic lagoonal barrier bar and shoreface deposits. And we saw all of those settings within 25 feet of core. And to me, what is most exciting is that these cores represent some of the classic reservoirs of one of the world's great petroleum provinces, the North Sea. So hopefully you'll leave this talk with a little more knowledge of the North Sea petroleum system and a fistful of new analogues to apply to your own reservoirs. And I'd just like to thank everybody for their attention and listening, and thanks to North Sea Core who supplied the core to me. Thank you.